For 140 nights a year, lightning flashes 40 times a minute, enough to power a city for hours. Yet no one knows why it keeps coming. The Catatumbo Lightning, Earth's most intense storm, blazes like a celestial beacon, hiding secrets in its endless flash. Midnight over Lake Maracaibo, the river delta glows, not with fire, but with light, blue-white arcs stitching the dark sky. Warm air from the Caribbean meets cool air spilling down the Andes. They collide. The air shudders. A storm ignites, not once, but endlessly. Russian scientist Andrei Zavrotsky arrived in 1991. He mapped the storm's birthplace, marshes near the river's mouth, trapped between mountain ridges. He saw the pattern. Cold air from the Andes, 12,000 feet high, slammed into the lake's warm, moist breath. The mountains acted as a lid, forcing the air upward. The collision charged the clouds. He called it a perfect storm machine. His theory had a twist. Uranium in the bedrock, he considered it, but the main force was geography. The lake, the river, the mountains, they were the stage. Later, a different theory took hold: methane from swamps and oil deposits. Scientists thought methane's symmetry fueled the lightning, but the storm's rhythm didn't match. It flashed most during rainy months, not dry ones as methane predicted. The evidence faded. In 2010, the storm vanished. For 2 months, no lightning lit the sky. Drought had gripped the region. Sailors, who once used its glow as a lighthouse, saw only darkness. Some feared the phenomenon was dying, but by 2011, it returned. The storm was not permanent, it was fragile. The mountains still breathe. The lake still exhales. The lightning still strikes 40 times a minute for hours. The cause is a dance: warm, cold air, rock. But why this dance happens here year after year with such relentless intensity, no single answer holds. Only the light continues, always. The mountains don't just surround Lake Maracaibo. They lean in, trapping warm, moist air rising from the lake and Caribbean Sea like a lid on a pot. Cool air spills down the Andes, 12,000-foot ridges, Parajá Mountains, Merida Cordillera, forcing the warm air upward in the same precise spot. This collision happens over the specific boggy delta where the Catatumbo River meets the lake. Air shatters. Electricity builds. Day after day, the same storm forms. The lightning isn't random. Its geography made visible. A relentless display of 16 to 40 flashes per minute, 9 hours nightly, across 250 strikes per square kilometer each year. Sailors once navigated by its glow. The methane theory holds the strongest scientific weight. Swamps and vast oil deposits beneath the lake exhale methane gas, a symmetric molecule that may facilitate electrical discharge. Early studies linked methane concentrations to peak storm intensity, but the storm's timing contradicts this. Methane should surge in dry months, January to February, but the lightning peaks during heavy rains in April and September. This mismatch means methane likely plays a supporting role, not the main cause. The storm's rhythm defies simple gas chemistry. Uranium in the bedrock was another hypothesis. Radioactive decay could ionize air, sparking lightning. Yet this theory crumbles under scrutiny. The storm vanished during the 2010 drought when groundwater dropped, yet uranium levels wouldn't change instantly. The uranium idea explains nothing about the storm's seasonal shifts or its sudden absence. It's a footnote, not an answer. The leading explanation is the mountain lake atmospheric dance. The Andes, Parajá, and Merida Cordillera form a natural bowl, trapping moisture and forcing constant air collisions. Scientists from Universidad del Zulia analyzed decades of data, correlating lightning bursts to wind patterns over the lake and temperature shifts in the Andes. They tracked how the storm's location shifts slightly with the seasons, always returning to the same geographic trap. Yet the why remains elusive. Why 40 flashes per minute? Why did the drought extinguish it for 2 months? The mechanism is clear. The full story is, the mountains still breathe, the lake still exhales, the lightning still strikes, always. The methane theory suggested oil deposits and swamp gas sparked the lightning. But the storm peaks when swamps flood, not when they dry. Methane emissions would spike in January-February, the dry season, yet lightning drops then. In April-May, floods drown the swamps, methane should surge, but lightning explodes. The data contradicts the gas model. It's like a clock ticking backward. In 2010, droughts silenced the storm for 2 months. Lake levels fell visibly, swamps cracked like old pottery, and the lightning vanished entirely. Uranium levels in bedrock wouldn't change overnight. Methane production would barely stutter. The storm didn't fade, it simply ceased. This abrupt end ruled out slow-moving causes like bedrock decay or gas seepage. The drought was the final, clear evidence. The mountains form the stage. Andes, Perejá 3,750 meters, and Merida Cordillera create a natural bowl around Lake Maracaibo. Warm Caribbean air meets cool Andean winds over the lake's heat haze. This collision happens consistently near 8 degrees 30 and 71 degrees 0, the exact spot where the Catatumbo River meets the lake. Universidad del Zulia tracked how the storm's epicenter drifts slightly with the seasons, always returning to this geographic trap. The mechanism is visible, the why is. All theories map the mountains and lake, but they miss the spark. Why does this specific spot hold 40 lightning flashes per minute? Why did 2 months of dry air extinguish it completely? The storm's rhythm syncs with humidity, not methane or uranium. Yet the geography stays unchanged year after year. The mountains still breathe, the lake still exhales, the lightning still strikes, always, but the full story, why this intensity, why it can vanish, is hidden in the next storm. What will it take for us to see the whole storm?